let's return to our doctor scenario and see if we can figure out what exactly the probability of having cancer is given a positive test result. So, to summarize up here in this box, this is just the information from the problem. And we want to know what is the probability of cancer given that a test is positive. So, think back to your experience with conditional probability and with these probability tables. Remember, the cells in the middle are the joint probabilities, and the cells on the outside that represent the sum across rows or down columns are the marginal probabilities. So hopefully this makes sense to you. We have test positive, the probability of testing positive, the probability of testing negative overall, and here we have the probability of having cancer and the probability of not having cancer overall in the gray marginal boxes. So we can put it in there like this. This is how we denote the marginals. Probability of C, probability of not C, probability positive, probability negative. Good so far? All right. So here's our joints. Here are our joint probabilities, just like in the previous video, the example with hair color and eye color. Well, here, this is the joint probability of having cancer and testing positive. That sounds like something we're interested in. Here's the joint probability of having cancer and testing negative, not having cancer and testing positive, and not having cancer and testing negative. These are our joints. Great, perfect. So let's look at the information again and take stock of what we have and what we need. We are given the base rate for cancer, the probability of cancer in the population. That's 1%, or 0.01. We are also given that people who have cancer, so given that you have cancer, you have an 80% chance of testing positive, or 80% of people who have cancer will test positive. That's represented by this conditional probability right here. We also have this information. So given that you do not have cancer, the probability of testing positive is 7%. So, oh, bollocks. I bollocksed it up. Okay, sorry about that. So this is now accurate. We have the probability of testing positive, given that you do not have cancer, is 7%. Great. So this is all the information that we're given. But, based on this information, we're also sort of given this stuff. So we know that in our population, you either have cancer or you do not have cancer. If there's a 1% chance that you have cancer, well, there's a 99% chance that you don't, since those two things are mutually exclusive. Likewise, the probability of testing positive given that you have cancer, that's 80%. But given that you have cancer, the probability of testing negative has to be everybody who doesn't test positive. So since those two things, testing positive and testing negative, are mutually exclusive, then same thing, they have to sum up to 100% of the population. Well, 80% plus 20% gets us to 100%. And same thing here, if you do not have cancer, testing positive or testing negative has to sum to 100%. So we just do 1 minus this, 0.07 to get 0.93, 1 minus 0.8 to get 0.2, and 1 minus 0.01 to get 0.99. Excellent. Well, what do we want? What are we looking for in this problem? The probability of cancer given a positive test. So given that we have a positive test, so we're looking in this column, and having cancer, well, we're looking in this cell right here. So it would be this out of the total of all the people who test positive. So the people who have cancer and test positive out of everybody who tests positive. We can represent that like this. We want the probability of cancer given a positive test. And we know from both our derivation of Bayes' rule and from just the basic statement of conditional probability that the joint over the marginal is the conditional. So that's just what I said, except here in symbols. We have the probability of this joint over the probability of this marginal. But what are these two things? We need these two guys. We need the joint and we need the marginal. How can we find them based on what we're given? Well, remember this formula. This formula right here tells us that each of these joint probabilities can actually be expressed as a marginal times a conditional. There, we just replaced them all with the marginal times the conditional, the appropriate one. So the probability of having cancer overall times the probability of having cancer given, or testing positive given that you have cancer. Let's start filling in this table based on the information that we know. We know the probability of having cancer is 1%. So that would go right here in the margin. We know the probability of not having cancer is 99%. That would go right here. So boom, there those guys go. What else do we know? Well, we can figure these out, can't we? Because we know this is the probability of having cancer, and we know this is the probability of testing positive given that you have cancer. So that's this times this. Great, so 0.01 times 0.8 is 0.008, or 8 thousandths. That's really 0.8%. So what else do we know? We also have this marginal, and we have this conditional. That's right here, the probability of not having cancer times the probability of testing positive given that we do not have cancer. This times this, right? Let's put that in. Great. Now then, we know that this marginal right here means when we sum this joint with this joint, we have to get this value right here. So we can figure both of these out easily based on just this minus this gives us this one, and 0.99 minus this gives us this one. Great. We could have also found them out using these. Either way, both ways are legitimate. Now we can sum down the columns to find these other marginals. So this plus this will give us this one, this plus this will give us this one. Great, so we filled out the whole table. We didn't really need to do this, but it was a good exercise because these tables are extremely useful. Great, so just to kind of reduce the clutter, we can keep only the values. Now how do we find this? How do we find the probability of the probability of cancer given that the test result was positive? How do we find that? Well, the joint of positive and cancer over the marginal of positive, right? This right here, which is just this, which is just this. So this over this gives us 10.34%. So the probability of actually having cancer, given that you got a positive cancer test result, is only 10.34%, just over 10%. Shocking. There's another way to think about it if the tables aren't doing it for you, and that's using tree diagrams. So this is the way that I was actually introduced to Bayes' rule in a textbook a long time ago. And it started out like this. It said, okay, if you're right here, then these two things have to add up to 100, right? Having cancer and not having cancer. So 1% and 99% make 100%. But so given that you have cancer, there are two possible outcomes. You either test positive or test negative. So these are the conditionals. Given that you have cancer, the conditional probability of testing positive is 80%. Great. So these are familiar things, just represented differently. Likewise, given that you do not have cancer, the probability of testing positive is 7%, and the probability of testing negative is 93%. To find the joints, we just multiply. We multiply the probability that you have cancer times the probability that you test positive given that you have cancer, and that gives us 0.008, or 0.8%, like we saw in the previous slide. Doing this for all of these just fills in those joints, just like in the table. Now, finding the probability that you have cancer given that you test positive based on this information is now pretty easy, right? Because this is our joint, testing positive and having cancer, over what? Over the probability that you test positive, right? The marginal. That's this one plus this one. This one tests positive, and this one tests positive. So out of all the ones that test positive, we're only interested in the fraction of those that also have cancer. So writing it out, this over these two summed up gives us 10.34%. just like we saw in the previous slide. So either way, either method works, whichever one you feel more comfortable with. Both are really useful to know, though. I'm going to leave you with a question. So the probability that a person is male, given that the person smokes cigars. Let's say that 49% of adults in a certain population are male. And further, let's say that, given that a person is male, 9.7% smoke cigars. Also, let's say we know that 1.7% of women smoke cigars. If we randomly smell cigar smoke, what is the probability that a male was the person smoking a cigar? Think about this for a second.